So, to start today and sort of get us back thinking about this idea of sampling distributions, which we barely touched anything on so far, I want to go back to the Tuesday before Thanksgiving where you guys were each getting samples of Starburst. And so, for example, like one of you, I'm pretty sure it was Braden, got a sample that had it had 4 pink out of a total of 5. And then what we did is we had each of you take your sample of 5 and your sample of 10 and then your sample of 24. And so you guys, you can see the graphs at the front of the room. I'm making this video from my house, so I can't bring them out in front of us right this second. But, okay, so when we talk about this, this proportion of pink, 4 out of 5 is 0.8, okay? That is a p-hat in that it was a proportion not of the entire bag of Starburst, but rather just of an individual sample. And so the graphs, which I believe are still in the front of the room, you know, we had some graphs, some p-hats. Let me just kind of get my axes labeled here. Again, the ones on the front of the room are more accurate, but if you guys remember, we had like a dot here and a whole bunch of dots at like 0 and 2, and then a few 0.4s, a few 0.6s, and 1.8, something like that, okay? And, all right, and so what I want to point out is that each and every single one of these is a p-hat. Each of you took a different sample, and your different samples each have what we call variability, okay? And if it doesn't matter whether you look at the graph of this is an example of that was from memory similar to n equals 5. If we looked at n equals 5, n equals 10, n equals 24, if you look at any one of those graphs, if I asked you to use the graph to estimate like what is the proportion of the bag that is pink, I think most of us would say 0.25 because we look for what this average of this graph. And so there's a whole bunch of, sorry, interrupted by the dogs for a hot second, guys. Okay, so the graphs can kind of tell us this like p equals 0.25, but that when we're talking about that p, for that, p would equal what I would call the true proportion of pink. In other words, the proportion of pink of the entire bag of Starburst, if that's our population. And we each got different p-hats because we each took samples. And as we've been talking about for a couple weeks, what we know for sure is that samples, no matter what we know about them, are not perfect. So again, if you want to repeat out loud, samples are not perfect. I'm sure you guys repeated out loud with me. So a couple of things that I want to really emphasize from this is that no matter what, there is only one value for p, but there's lots of possible values for p-hat. So when we take a sample, p-hat is a variable. In that we get different samples, so we get different p-hats, okay? P is a constant. Now, in the real world, you know, like when you think about algebra class, a variable stands for a number you don't know and you're trying to solve for. And in statistics class, variable means something different. So in this context, typically we know p-hats. We can take a sample and measure our sample, and we use it to talk about some unknown constant that we don't know about, okay? Now, I didn't have us do this because I didn't want to go get the balances from Dr. Lee. We could also have taken each of our Starbursts and asked, like, weigh them in grams, right? So you could take the average grams of, say, your 5 Starbursts. And what we would do is say, well, what does that make the true mean grams of all the starbursts. All right, and again, so X bar would be our sample mean, and each of us would take a different sample, get a different sample mean. That would be our variable, and the true mean would be our constant that we are trying to estimate. Okay, so we've kind of talked about the values, our statistics, the ones we measure from our samples, our variables. So I want to talk a little bit more about what we call sampling variability. So let's say that Mr. Belk wants to estimate how much time sophomores and juniors spent studying for the ACT. So what they do is, or for the PSAT. So Mr. Belk takes a random sample of 10 students, okay, and asks them how many times, and he finds that the mean for his sample was 3.2 hours. All right, now, let's say Mr. Stork does the same thing. He takes a different random sample of 10 students, and his X bar works out to be 2.6 hours. Okay, and if we wanted to, we could start building a dot plot that is mean hours studying. And let's see, let's say the lowest amount is 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, okay? And so, for instance, Mr. Belk's sample would be at 3.2, and Mr. Stork's sample would be at 2.6. And then, just for fun, we're going to say, hey, Miss Meister is a great big statistics nerd. She's also going to take a random sample, and she's going to find that her sample was 3.8. And then Mrs. Turner doesn't like to be outdone by Meister, so she's going to take a sample, and her sample was 2.6. And then all of a sudden, every single teacher takes a different sample, and we have a whole bunch of different random samples for the mean hours people spent studying. Okay? And let's go ahead and say that this graph kind of represents every single person, every possible sample. Okay, so samples don't all have the same mean because samples are not perfect. They have sampling variability. We didn't do anything wrong, right? When you take a sample, okay, let's go ahead and say that the actual mean spent studying is right at 3 hours, and none of our samples were right at 3 hours. Okay, that doesn't mean anything about our sampling process being wrong. By the way, that would mean mu equals 3 hours, just to get practice using those things. It's that we have variability just to the fact that we're using random chance to create our sample. Okay, now if we go back for a little bit and some different samples, one of the things I want to talk about is so this is what we call a sampling distribution. A sampling distribution, by definition, is a distribution of measurements and when I say measurements, guys, I'm talking about, say, a sample mean or a sample proportion, okay? It's a distribution of measurements taken from a large, arguably infinite number of samples from a population. I'll give you guys a second to get that down. Again, it is a distribution of measurements taken from a large number of samples from a population. Okay. All right, now some things that we're going to pay attention to is that if it is a distribution, it has a shape, it has a center, it has a spread. And since in that spread that we're talking about is this sampling variability that we're going to measure using something similar to, well, it is a standard deviation, okay? So this last idea is just to explain why we call the standard deviation of a sampling distribution as a special name. We call it the standard error, and I'm going to kind of explain why we call it the standard error, okay? And we're going to use this graph to kind of talk through that. Okay, so in some respects, standard deviation as we understand it so far, has always been each value has a distance from the mean, right? And so, for instance, this X bar has a fairly large distance from the mean. This one has a very small distance from the mean. These two do. This one's a little bit bigger, okay? And that distance from the mean, the standard deviation is the average of those distances. Well, when we look at this picture, those distances are how far my sample mean is from my population mean. That's what, and so the standard deviation is the average distance X bar is from my population mean, okay? And since our goal is always to be using that statistic, whether it's X bar or P hat, to estimate the population value, that's going to be our goal over and over and over again, is to use the sample mean to make conclusions about the population mean, okay? So the standard deviation is the average error due to sampling alone. Okay, so we would expect that our sample doesn't perfectly match our population. It is off by a little bit, so there is error in sampling, okay? And the standard deviation of a sampling distribution, okay? This is a lot of heavy theoretical stuff. Distribution of measurements, that's basically representing all the possible sample measurements we could take. And how does it relate back to how far is it from the population value? That is my average of those distances is my sampling error, which is represented by the standard deviation of the sampling distribution. We'll talk about this a whole lot more. I know this is a pretty heady topic. So make an attempt now, guys, to work through some of the homework and the review page if there's time at the end of this video. And I will we'll go into a lot more detail with this when I get back on Wednesday. Have a good one.